Woohoo, college. All right, let's chat a little bit. I'll let these guys have their fun. So let's talk a little bit about Newton's laws, right? We already talked about the first two, but now we need to introduce Newton's third law, which is sort of simple to state, but rather complicated to understand. So let's go back to the first two. Anybody here remember what the first one was? And why don't you do me a favor? Can you guys hit your mic button on your tables? Just push it once and it should turn green. If you push it and then wait 1 second, it should turn green. Anybody getting that word? Okay, good. So first off, let's give a round of good mornings to everybody at home. If you have somebody's personal name that you want to shout out, go for it. Good morning.
Sup, Cody.
Good morning. Good morning.
Hey, Caesar.
Okay.
What are you doing with the whiteboard?
Now, anybody remember what Newton's first law was? What was Newton's first law?
Object in motion tends to stay in motion.
Hannah got it exactly right. Object in motion tends to stay in motion. Okay, we know this, right? If you drive in your car and you take your foot off the accelerator, you don't come immediately to a stop. You tend to stay in motion. Objects in motion tend to stay in motion. Likewise, objects at rest tend to stay at rest. Okay? Number two is the one that we are really having a lot of fun with now. Hopefully. You guys having fun with it? I'm having fun with it. Newton's second law, right? Net force equals the mass times the acceleration. All right, we better rein these guys in because they are spending way too much time drawing colored boxes. Which is great when you get like 100 people and they all have the same white room availability, right? Somebody does some beautiful artwork and then immediately somebody else erases it and puts a block over it. Force goes like acceleration, right? If you push on a block, it accelerates. This is not force goes like velocity. This is force goes like acceleration. Remember that question from your last midterm. It was talking about if you're in an elevator and you feel heavier than you normally do, is that elevator moving upward or downward? What'd you guys put? Okay. Some people saying up, some people saying down. The correct answer was you cannot tell if it's moving up or down. Okay, that was the correct answer. Why? Because think about it. When you're on the first floor and the elevator starts moving up, you feel heavier. In that case, the elevator is moving up. But if you're on the top floor and you're coming down and you come to a stop at the bottom, then you also feel heavier. That elevator was moving down. And this is an important point. Force goes like acceleration. It doesn't tell you about the velocity. It just tells you about the change in velocity. So you really have to know what the initial conditions are to calculate the final velocity. All right, F equals ma. We've had a lot of fun with that in the last chapter, and it will hopefully continue. All right, number 3. Newton's third law, right? This was sort of the big 3 that he came up with. What was the third one? Anybody remember this? You guys probably remember this from growing up. Somebody probably said this to you at some point. You might not realize that it's really Newton's third law, but anybody have a thought on this? Okay. No, not energy is conserved. We're going to get to that one later. Yeah?
For every action, there's an equal or opposite reaction.
Right. It's the action-reaction law. For every action, there's an equal and opposite reaction. Why do you know this? Because your parents have undoubtedly used this at some point in your life. Why are you grounded? Because that's my reaction to your action. For every action, you throwing the rock through my window, there's an equal and opposite reaction. I take away your phone for a month, and you lose the rock. Okay? Another way to say this is no isolated force exists. No isolated force exists. If we have a force, there has to be something else accompanying it, some other force accompanying it. Okay? So, how do we understand this? One way to understand this is the following. Let's say we have two masses, M1 and M2, and they are just floating in outer space. Is there a force between the two? Sure. Gravity, right? Pretend this was two big planets. They would be attracted together by gravity. There is a force, F12, which is the force on 1 due to 2. Okay? M2 is trying to pull on M1. But Newton's third says you can't just have that one isolated force. There has to be another force, F21, which is the force on 2 due to 1. So if M1 is getting pulled to the right with a force F12, M2 is getting pulled to the left with a force F21, and Newton's third says this. Okay, this is the point of Newton's third law. F12 is minus F21, equal and opposite. All right. That maybe makes sense to you in terms of these planets floating around in outer space, but let's come back down to Earth and talk about something a little more tangible. Let's talk about a box on a table. So here's my table. Here's my box on the table. And now let's identify the forces that are acting on the box. So if I think about this box as my object of interest, we can identify the forces that are acting on the box. What forces are acting on the box? Gravity, right? We like gravity. We always draw gravity first. mg. What other force is acting on the box? The normal force from the table. So we got to be a little bit careful about our subscripts now. So let's write it as the following. NBT. The normal force on the box due to the table. Okay? Normal force on box due to table. Okay, gravity's trying to pull it down. It doesn't fall because it's at rest. The normal force on the box due to the table is what's holding it up. Okay, but we don't have anything that looks like this yet, right? If no isolated force exists, we got to have something else here to go with it. What else do we have? Let's think about the table. If the table is our object of interest, we can write the forces that are acting on the table. And the forces that are acting on the table are gravity, mass of the table times gravity. What else? Normal force from what? Okay. Normal force of the Earth acting on the table. So this is normal force on the table due to the Earth, right? The legs of the table are on the ground. The Earth is pushing up on it to keep it balanced. Is that it? Okay. Hit your mic, Sagar. Say that again, Sagar.
Sorry?
What else are we missing?
I think the mass of the box and the normal force the
Okay.
table applies on the box. That would be in that system too, right?
Okay. So gravity is certainly pulling on the box, but now we're looking at the table. And the box is a separate mass from the mass of the table. So I don't want to draw mg where that would be the mass of the box times gravity, but you said something else there, which is this normal force,
Yeah.
right?
Yeah.
As the table is pushing up on the box is pushing down on the table. How hard is it pushing down? It is NTB. So NTB is normal force on table due to box. Okay, that's what we need right there. Now, you're right, if everything is at rest, the magnitude of NTB is exactly equal to mg from this first equation. Okay? But when you write it out, be very explicit about this. So in the chapter, we talk about an action-reaction pair. And those are two forces that go together according to Newton's third law. So in our picture here, what is the action-reaction pair? It's NBT and NTB. Just like we wrote over here for the two planets, right? Now the action-reaction pair is the normal force in between the two. There's a normal force on the block, which is exactly equal and opposite to the normal force pushing down on the table. As the table pushes up on the block is pushing down with exactly the same magnitude on the table.